Okay, hello everyone. I'm back. We're back from our break. So what we're gonna go right into chapter 3. So I need to need to close this. I want to save the oh, sorry about that. This is newer computer for me, so getting used to it. In here, let's see if I'm able to. Hopefully, I can use the mouse now. So once. Other work. Yeah, we're going to keep the annotations because I want to provide that to you. All right. That's good. So we have that. Let me pull up the PowerPoint slide. And we'll start sharing that. We'll go to current slide. Oh, I have to enable editing. Okay. Sorry about that. I have to enable editing, otherwise it won't let me write on there. That will work. There we go. There we go. Let's pull the keyboard off of this then. Use it as a tablet. All right, so we are going into chapter 3. Chapter 3 is acids and bases. You might have seen acids and bases in general chemistry, but we're going to have a review in this class too. So an acid, so the Bronsted-Lowry defines acids as, you can be a proton donor or proton acceptor. And so my pen on, it should be, yeah. So you have the proton donor here, you have a proton acceptor. We can do this. Water can even donate and accept protons. We won't talk about that, but this is a classic general chemistry example, and this is a strong acid. This can be a base. This can be an acid sometimes too, but in this case, this is a base. It can accept that proton. And recall, why is there a positive charge right here? Oxygen should be 6 minus 5 equals positive 1, right? So you have 1, 2, 3, 4, 5, and that's how you get your 5 right there, and plus 1. In chlorine, if you go on the periodic table, it should be 7. You count 8 electrons around there, that's how you get minus 1. I'm trying to go to the next slide. It's not letting me. So a conjugate acid results when a base accepts a proton. So this would be the conjugate acid, and this would be the conjugate base. Oh, I didn't want to do that. So curved arrows, so the making and breaking of bonds involves electron movement, and they're kind of showing this right here. So this base is going to take a proton from this acid, and we have this right here. And mechanisms is the same thing as this proton transfer right here. We might have a carbanion. It's going to go attack a functional group. Let's just say this. It's going to start moving electrons, or it's going to take a proton. So there's many different things that it could do. And sometimes you'll have a hydride. This hydride will be negative, and this will go attack a spot that has a positive center. we talked about, maybe this carbon has a positive center, so it's going to go attack that, and then, it's going to become neutral. Here they're just showing you this right here, they're just showing you, acetic acid, it's a weak acid. So the base is attacking the acid, and you get the conjugate acid and the conjugate base. And the more important thing is to see how the electrons are being transferred. There's a minus charge right here because 6 minus 7 equals -1. That's how you get the, oxygen should be 6. You count around here, you get 7, and you get -1. So it's going to become neutral when it takes that proton, but then those electrons are going to be donated onto that oxygen right there. So then we get a -1 right there. So we're just showing the transfer of electrons. Again, transfer of electrons right here. What's going on right here? So once this group takes this, so this is acidic group right here, H3O plus. You can kind of see why that's a plus, because you get 6 minus 5 equals +1. But takes that proton. Now this becomes a neutral atom. This becomes, or not neutral atom, neutral molecule, water. And water is a pretty good, it's a good leaving group too. And we formed water right here. So we're going to have water leave right there. We subtract the water out. And now we're going to form a double bond. And this water can attack this proton right here to form that double bond, because there's a, in this instance right here, remember, if this leaves, I'm going to start erasing some stuff. It's getting a little messy. If this group leaves right here, what do we have? What we have is, we have a positive charge right here, but recall that there's 3 protons right here, right? So what's going to happen? How are we going to get rid of that carbocation? Well, another water group out there is going to come in. It's going to take that proton. It's going to transfer these electrons. And now we formed an alkene, which is a carbon-carbon double bond. So I'm just going to leave it right there. Just let me know if you have any questions about that mechanism. So this is kind of an introduction to you for mechanisms too. All right, I don't see any questions. And let me make sure I have the chat open. Yep. If you have any questions, I don't see the chat, just give me a shout out. So, there's a class on quantitative analysis, that goes over pKa values. We'll go over that a little bit, but we won't go too much into that. And, pKa equals, minus the log of the Ka. pKa equals minus the log of a Ka. And this is base 10, but like I said, there's a class dedicated to that. They're just going over and showing you how you get the equilibrium constant for this. So K equilibrium equals the products over the reactants. So we have products over reactants. And there's no superscripts right here. I mean, the superscript is 1. That's why you see the 1s right here. I should put them right there. No, actually, they go right up here. Sorry. I wonder if it's still on the eraser. So if there was a superscript 1, it goes up here. Since water is unity, it's going to be 1. Anything divided or multiplied by 1 is 1. So that's why it gets right here. So if the acid is strong, will Ka be bigger than 1 or smaller than 1? Well, if you just do the math, it's going to have to be larger than 1. all they did right here was they took the log. It says so Ka values range from 10 to the minus 50s to 10 to the 10. So the size of these numbers is very large or small. And so to bring this up to scale, they take the log, the minus the log. So if you take minus the log, you're going to get this equation right here. pKa equals minus log of the Ka. So just showing you how to derive that equation. And they give you different pKa values here. So this would be the strongest acid up here. Notice that the pKa values is -9. It goes all the way, in this table, it goes up to 9.3. And since these two differ by 2 units, they differ by 2 units. That's why it's 100 times stronger. 10 squared equals 100. If they differed by 3, it'd be 1,000. So you can use these pKa values to compare the strengths of the bases. The stronger the acid is, the weaker its conjugate base. So this would have the strongest base over here. If we just go, if this is the strongest acid, this would be the weakest conjugate base. So you can kind of make some predictions of, which direction the equilibrium is going to go. And the reason why they have a longer arrow right here, as opposed, oh, that's kind of in the way, isn't it? Note that this is longer, and the reason why it's longer, it has a smaller pKa value. So if it has a smaller pKa value, that means it's more generally going to go in this direction for equilibrium. So equilibrium favors the weaker acid and weaker base. So the higher the pKa equals the weaker acid. So let me think about that. Yeah, that's right. So weaker. So I did have it going in the right direction. Yeah. Here we see that the differences between the pKa values is much larger. So there's going to be a lot more products and reactants. This has a smaller pKa, so it's going to have a stronger acid. And it's generally going to be going just to the right. This is a carbanion right here. So you see that carbanion, it's taking that proton, and then, it's going to, put those electrons right there. So this is a conjugate base, and now it has that proton right there. So think about this, carbon wants to have, it wants to be net neutral. So, this is more favorable of a reaction. They're not showing you these 2 protons right there, but there's 2 protons right there. 4 minus 5 equals -1. That's how you get the -1 right there. So the stronger the acid, the more stable its conjugate base. When the acid loses proton, it forms a conjugate base, and we saw that, if we have H3O plus, this would be H2O plus a proton. That proton will usually, some carbon or something will take that proton, doesn't have to be carbon. And determine the stability of the conjugate base, we're actually looking at the stability of the lone pair. Here we're talking about stabilization. So the more effectively a conjugate base can stabilize its negative charge, the stronger the acid. 4 main factors affect the stability of a negative charge. We have resonance. Remember, we had this one double bond here, and we could go here. So we'd have resonance right here. Induction, and the type of orbital where the charge resides. So the type of atom that carries the charge, in order to compare the acidity of the two compounds, we need to draw and then analyze the stability of the negative charge. So you remember the electronegativity chart. So this is coming back. So according to the electronegativity, it'd be more stable to put the electrons on oxygen than it would be on a carbon. So it'd be less stable. The carbanion is less stable. It's going to really want to take a proton right away or to go somewhere. It says when moving down a column, size is the most important. The larger the atom, the more stable a negative charge will be. And the more electronegative atom. So not only, in this case, oxygen is going to be the more electronegative atom. Now, if this were sulfur, this would even be more stable because it's bigger. It's a bigger atom. And they're just showing you, if we, less stable, less acidic. And this would be more acidic right here because you can stabilize that charge on that oxygen more than you can here. Resonance. So, this has resonance right here. We have that double bond. We can do this. If we do that. We have some resonance. Right? So it's able to, spread that around. So the charge is more delocalized, it's more stable. So this would be less acidic. And why is that? There's no resonance here. Here we have, we have the capability of resonance, which is delocalization. So induction can also stabilize the formal negative charge by spreading it out. So these are electron withdrawing groups. The carbon is electron donating group. Why is chlorine electron withdrawing? You can think about the electronegativity chart. It all comes back to this. That's why this is really important. So it's going to withdraw electrons here. So it's going to be able to give this up more easily. I think that's a good stopping point today. So if you have any questions for me, please stick around. If you have any questions about the lecture, go ahead, please ask right now. Does anyone have any questions about the lecture or the homework? All right, so let me need to put this on the keypad. It won't. Apologize for this is a newer, here we go. Stop sharing. Stop recording.